In this video, I will talk about the deflection of beams using moment area method. This method is quick and easy compared to the double integration method. Now let us see what is this moment area method. From the deflection equation, we know that EI into d square y by dx square is equal to m. Okay. If we integrate this equation, we will get dy by dx is equal to 1 by ei times integral m into dx. Okay, so to find the slope, dy by dx is nothing but the slope. So slope is nothing but the area under 1 by ei times the area under the bending moment diagram. For example, if we have any function y is equal to f of x. Okay, here is our x-axis and here is our y-axis. Let us say any function is there. This is y equal to f of x, and integrate. If we integrate this function f of x dx with respect to between any 2 points a and b, we will get the area under this curve. Area under this curve between points a and b, right? Similarly, to find out the slope between any 2 points, slope difference between any 2 points is the area under the bending moment diagram divided by ei. So the slope is equal to, we can write as 1 by ei times area under bending moment diagram. Okay. Similarly, if we integrate this one more time, we will get the deflection, right? So the deflection y is equal to 1 by ei times, if we integrate this one more time, this will become m into x. That means moment of bending moment diagram, 1 by ei times moment of bending moment area. If we do this, we will get the deflection of any beam. Okay, now let us consider any beam, any cantilever beam like this, and let us try to find out what is the slope and what is the bending moment, and what is the bending deflection. This is the cantilever and we are fixing here and we are applying a load here P, and here is our length L. Okay, if we draw the bending moment diagram for this, it will be something like this. This is our zero line, Here is the bending moment. Here is 0 because load is here. Load is passing through the point. So load into distance, which is 0. But here we have the bending moment P into P times L. So here is P into L is there, and I'm joining these 2 points through a straight line. Okay, because the bending moment function is, if uh, at any distance x, we consider any at any distance x, m is nothing but p into x, p times x. At x equal to L, bending moment is p into L, and this is the first order equation. So I'm joining these 2 points through a straight line. Now area of this bending moment diagram is nothing but of length into this one into this length into PL into 1 by EI. I'm just using this equation, 1 by EI times area under bending moment diagram, 1 by EI times area under bending moment diagram. That means this area. This is nothing but the slope dy by dx, dy by dx, the slope is equal to P into L square by 2EI. This is what we got in the using double integration method also. Now let us try to find out the deflection. Deflection y is equal to 1 by EI times moment of bending moment area. This is our deflection y. This is nothing but 1 by EI times moment of bending moment area. Okay, here bending moment area is nothing but 1 by 2 times PL into L. This is the area. We want to find the moment of this area with respect to point where the slope is not zero. That is, if this is our deflection curve, right, and here is where our deflection is 0 and slope is also 0, so we have to take moments about this point, that is this point. Okay, so if we take the moment of this area with respect to this point, its center of gravity of this area is somewhere here, and the distance from here to here will be 2/3 of the total length L. So this area into distance will give us the moment of bending moment area. So this area into this distance, 2/3 of L, thirds of L. This is nothing but P into L cube by 3 into EI. This is what the deflection of beam, the maximum deflection for a cantilever beam, P into L cube by 3 into EI. Now using the same method, let us try to find out the slope and deflection for a simply supported beam. Let us take any simply supported beam, something like this. Okay, here at this end we have hinged support, and here we have a roller support. Here is our hinge through which it can rotate easily like this, and here it is resting on a knife edge, and this knife edge is free to move in this direction. Okay, and we have a load in the center which is P, and the total length of the beam is L. This beam is, let us say, made of material with Young's modulus E, and its cross section is having moment of inertia of I. Now we want to find out what is the maximum deflection in the beam. Okay, for that we are using moment area method. First, let us try to find out what is the slope. Slope is equal to 1 by EI times the area of bending moment diagram. Okay, now let us try to find out, let us draw the uh, bending moment diagram for this. Before that, let us draw the free body diagram for this beam. Since there is a load P here, this load is acting in the middle of the simply supported beam, so this load will be shared by these two supports equally. This is P by 2, and here also we have P by 2. Okay, now the beam is in equilibrium. Now we can draw the bending moment diagram. This is our reference line where the bending moment is 0. Here the bending moment is 0 at extreme points, since loading to distance is 0. But here the bending moment is P by 2 times L by 2. This is our L by 2. So here the bending moment will be P into L by 4. And these 2 points I am joining through a line, straight line, since the bending moment diagram is a bending moment is a function of order 1. These 2 points I'm joining through a straight line. Okay, and we know that the deflection curve is something like this. We will have the maximum deflection in the center, and the slope at this point is 0, because if I draw a tangent at this location, it is a horizontal line, so the theta is 0, tan theta is 0, so the slope is 0. But here I will have the maximum slope. If I want to find out the slope here, I will just draw a tangent here, and whatever the angle it is making with x-axis, that into tan theta will give me the slope at this location. So we have 2 points. Here is A and B. The slope difference between points A and B is given by the area under the bending moment diagram between points A and B. Okay, so we have to find out the area under the bending moment diagram, this one, between the points A and B. Okay, so the slope at point A, slope at point A, dy by dx is equal to 1 by EI times, what is the area here? This is L by 2. Okay, so this is nothing but 1 by 2 times L by 2 into P into L by 4, which is PL square by 16 times EI. This is the slope. So this is the value we will get tan theta. If this is theta, tan theta or tan theta must be equal to this one. After knowing all these values, what is the length and what is the Young's modulus and uh, moment of inertia, we can find out what is the theta, that is slope here. Okay, that is P into L square by 16 EI is the slope for simply supported beam. Now let us try to find out the deflection in a simply supported beam, that is this one, how much it will deflect. Okay, so the deflection is nothing but 1 by EI times moment of bending moment area. Okay, is nothing but 1 by EI times bending moment area into distance. Moment of bending moment area means bending moment area into distance. Here bending moment area is just now we have calculated PL square by 16, P into L square by 16. Okay, and we know that the slope is here 0 and slope here is non-zero, so we have to take moments about this point. We have to take the moment of this area with respect to this point, non-zero slope point. Okay, here is our CG, center of gravity, and the distance here must be L by 2 into 2/3, which is L by 3. So this into distance is L by 3. This will give us P into L cube by 48 EI. This is the deflection for a simply supported beam. Now let us try to do some numerical problem. Let us say one cantilever beam is there of circular cross section. Its diameter is 50 mm or 5 centimeters, and its length is some 2 meters. It is made of steel. Okay, let us say one person is hanging here, a person with weight of 80 kg. Okay, now we want to find out the deflection at this location at the end, and we know that the deflection formula for cantilever beam is deflection is equal to P into L cube by 3 times E into I. Okay, as we said, this is made of steel. Its Young's modulus is equal to 210 gigapascal. Okay, now we want to find out the deflection here at this location. What is P here? P is 80 kg, which is nothing but 800 newtons, considering G as 10 meter per second square. Let us, in this formula, we have to keep everything in newtons and mms. Finally, we will get the deflection value in terms of millimeters. This is our p value, that is load value, and the length is 2 meters, right, which is 2000 millimeters, and Young's modulus is 210 GPa is nothing but 210 into 10 cube MPa. MPa is nothing, MPa or Newton per mm square. Okay, we are just trying to keep everything in newtons and mms so that this units consistency of units is very important, otherwise we will get the wrong answer. And finally, our I value, moment of inertia for a circular cross section about this axis, a axis which is passing through the center, okay, which is nothing but pi d power 4 by 64. Pi by 64 into d power 4. D is, diameter is 50 mm. Diameter is equal to 50 mm. So 50 power 4. If we do this, we will get 306919.6 mm power 4. Okay, finally we can substitute all these values in this formula to get the deflection. The deflection delta is equal to P is 800 into L cube is 2000 cube by 3 times Young's modulus 210 into 10 cube into I value is this one, pi d power 4 by 64, which is 306919.6. If we calculate this, we will get delta as 33 mm or 3.3 centimeters. That means if there is a rod completely built in with a length which is made of steel and a length of 2 meters, and its diameter is 5 centimeters, and if a person of 80 kg is hanging like that, it will be deflected by this much amount, 33 mm or 3.3 centimeters.